So,
Ooh, I can ask a lot of questions just from that slide. It's a good slide.
it is a good slide. So this is right out of your book.
Yes.
So the book chapter is really good on this one. You have the book chapter printed?
Well, it has the same picture actually.
Oh, in the
Well,
lab handout.
I think the lab handouts are from.
Yeah, they're probably like that.
Kind of, yeah.
Are they connected?
They are connected, yeah. There's pieces of those, all of them in the lectures, so. That's one thing that was all written as a bigger package, yeah. And so, yeah, and to do the slide sets, this is all of chapter 11, I just have the Gran plot stuck in the middle of it, with a few extra slides for discussing the lab itself, right? But I didn't even put procedure in on this one. The big thing, right? The volume of the base times 10 to the negative pH, okay? When you measure pH, you're measuring the activity of the hydrogen ion concentration. When you're measuring pH, you're measuring the activity of the hydrogen ion. And so when we're doing the measurements, this graph actually is not hard to make, okay? I know it says that this is the hard part, but you can make it harder than what it is. Okay, you with me? And so anyway, on the other axis, it's just the normal volume of the base. Okay, so we're titrating an acid, and all right. And then the slope of the line represents something that's very important to us, so this can also be used as an analytical procedure to find KAs for weak acids. Okay, so you guys are familiar with Ka and equilibrium expressions. And so this is the graph itself. And so looking at a very narrow volume range, in fact, they put this graph into microliters, okay? You don't have to do that. You can graph it in milliliters, just to let you know that, because that's what you're measuring with and it's more convenient. And so then what you're doing is when you graph the data points from the middle of that right at the end point, and you take the linear piece and put a line on it and extrapolate it through the x-axis, your endpoint is right there. Okay, so that's how you're measuring it. So to utilize this to find the endpoint and Ka is very easy because you don't have to do the activity mathematics. You with me? Now, the activity mathematics we'll do in chapter 8, chapter 9, something like that. We'll do an equilibrium chapter for review, and then we'll start activity, which is just an addition to. And so those activity coefficients that we're talking about are...
is that gamma?
Yeah, it's gamma is the symbol that they use for that. So this is the activity coefficient, right? You could also see it as an A sub H like this, and so that says activity, and those two are equal if you see that in terms of the relationship. And so then there's a mathematical relationship which includes ionic strength, and ion mobility and so on that we'll learn to calculate. It just adds to every problem that you're doing in terms of an equilibrium expression. Yes, Jacob?
There's a question about that, like, picture it was on our lab, but I was having trouble visualizing, like, what part of the curve. I know we're looking at the equivalence point,
Yeah.
but are we taking, like, for example, if we take the middle of the equivalence point, it would seem like it would be like the middle of the graph.
It is. You're using the middle of the graph, that slope.
But then why is it where
From
the
just the-
slope hits the x-axis?
Gran plot used data from just before the equivalence point, right? So in that steepest part of the graph right there, you take those points that are in that and use those to make the plot. And then that extrapolation of that line goes right down to the endpoint.
So it's just bending where that equivalence point.
Well, if you look at this plot right here, this is the equivalence point right there.
Yeah.
So this extension of the line shows where that bends.
So most of the graph is actually of stuff right before you go.
Mhm.
Alright, I'm following now.
Yep. And so this is the best way to do it.
Alright,
Right.
that makes sense.
So are we solving for Ka?
All you have to do is get the slope of the line. You'll have, well, a mathematical relationship to Ka.
Yeah.
So if we'll look at that. So, but if we consider this titration Ka, and you guys are familiar with concentration of the products over reactants, right? And so for an acid equilibrium, then H plus and A minus, or we can talk about any acid here, divided by HA, describes that relationship. And what you guys haven't seen before is these activity coefficients, okay? And so those have to be determined mathematically, and we'll teach you how to do that in chapter 8, okay? So, but we don't have to have those today because of the relationship of the graph. You guys know what the volume is and you know what the pH is, and so this is what you plot. Okay, so you don't have to have the familiarity, all right, to do that portion of the graph. Okay, to make the graph itself. And then we'll work on activity and add that so you can have an understanding of the remainder of the process. But anyway, so if I'm looking at all of this, it is necessary to include activity coefficients because pH electrodes respond to the hydrogen ion activity. And so when that's the case, then 10 to the minus pH gives us the activity of the hydrogen ion. Okay, so we can use that in our graph. And then the relationships of moles of OH delivered is volume of the base times that concentration, formal concentration, divided by the dilution factor. And so anyway, and then the raisal moles minus moles of OH divided by the total volume dilution factor, then that gives us the concentration of HA and the relationship when they're doing the titration. So you can actually measure these values. But ultimately what you're gonna do is take this equation and rearrange it into this form or the Gran plot form. And so if I do it in this form, then Ka times the activities become the slope, and then X is the VE minus the VB. And so that's that relationship. Okay.
So Ka times the activity coefficient, both of those over each other, that is the slope, right?
Mm-hmm.
So that's just y equals mx plus b.
Yeah, that's just y equals mx plus b, yeah, absolutely. And then you notice the x-intercept here is defined as the volume of equivalence.
That's
So,
pretty
yeah. So it's a lot cleaner than what the lab handout makes it sound.
Yeah.
Okay, oops, I just rang my phone, it's gonna start singing. Oops, where my phone's at, I guess I'll find it here in a minute. Oh, it won't because it's in airplane mode. Ha ha ha, tricked it, didn't I? So, so this is another Gran plot showing more along the lines of what we're gonna see. So this is one that was actually done. Do what? Yeah. And equivalence point is determined by determining where the y-axis equals 0 or x-axis, or the y-axis equals 0, the x-intercept. Okay. So the dissociation constant is found by determining the slope of the line generated by the Gran plot. So when you get your equation, you can set it to 0 and y equals 0 and solve for x, and that will give you the value of the Ka times the activity coefficients, and then we'll talk about activity coefficients, and someday you can solve for the Ka. How's that?
Yeah.
Does that work? So not necessary for it this time. Everything today is acid base, can go down the drain, will be neutralized to water. And any other questions? You're using your standardized base from that you previously made. If you need more Gabby made base, it's just not standardized. We'll have to standardize it very quickly. So, all right, that's all I got.